This is the Chapter 6 pre-class lecture video on the Fisher-Tropsch process. And so the Fisher-Tropsch process is a method in which coal is converted into gasoline. And so the first step of the Fisher-Tropsch process actually involves an old method that was used before the United States' big jump in conversion from coal to petroleum in the 1950s. Prior to the 1950s, a product was used to do things like run the street lights on a city street back in the 1920s or 1930s. Other things like provide the energy necessary for heating large buildings of apartments in major cities. And this product that was used as energy as an alternative to coal was called water gas. And water gas is produced from coal. And so it's considered like liquefied coal. That's why they call it water gas, because it's a liquid. So they're taking a solid coal and therefore converting it into a liquid fuel called water gas. And so the coal is reacted with steam under very high temperatures. And what's produced is carbon monoxide and hydrogen gases. And this mixture of carbon monoxide and hydrogen is called water gas. And then the Fisher-Tropsch reaction process takes the water gas and then uses a catalyst to produce hydrocarbon compounds. And of course, the side product being water. The most important hydrocarbon that's produced by this process, of course, is octane for the purpose of making gasoline. And so the Fisher-Tropsch process depends on a catalyst, and the catalyst lowers what's called the activation energy for this reaction by providing an alternative pathway for it to occur. This water gas reaction would never happen. This water gas would take a very, 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 very long time for this water gas to convert itself spontaneously to hydrocarbons and water. But adding a catalyst to this Fisher-Tropsch process speeds up the rate of this reaction. And it does so by lowering what's called the activation energy. The activation energy is the energy needed to initiate a chemical reaction. So starting off, the activation energy for taking water gas and turning it into hydrocarbons is a very, very high activation energy. What the catalyst does is lowers that activation energy requirement, making the reaction go at a faster rate. So the whole purpose of the Fisher-Tropsch reaction using that catalyst is so that you can quickly convert the water gas into gasoline. And so this figure is called an energy profile diagram. And so without using a catalyst, you have an uncatalyzed reaction. You have a very large activation energy. And therefore, the reaction is going to proceed very, very slow. However, a catalyzed reaction is going to have a much smaller activation energy. And therefore, the catalyzed reaction, shown here in blue, it proceeds much faster. And therefore, you get products much sooner by using the catalyzed reaction versus the uncatalyzed reaction. And so what this is the starting energy level. And then when you get to products, this is your final energy level. And then what this red arrow is the difference in energy, or the change in energy between reactants and products, which we call delta H. And so this particular reaction is exothermic because the delta H is negative. You start off at a higher energy level, you end up at a lower energy level. So the delta H, the final energy, minus the initial or starting energy, is going to be a negative number. And that will make the reaction exothermic. And so again, we're just repeating our same Fisher-Tropsch reaction here. I forgot to write that in on this problem. So that's 2N plus 1 CO plus N amounts of H2, producing CN H2N plus 2. That's a hydrocarbon, and in particular an alkane, plus N number of water molecules. So when N is equal to 1, then our reaction, 2 times 1 is 2, plus 1 is 3. I wrote that. It's 2N plus 1 H2 plus NCl. So if N is equal to 1, we've got 3 H2s plus 1 CO, producing, if N is 1, then that's methane. So determine the heat evolved by this reaction if N is equal to 1. So to do that, we've got to find the delta H. And so the bonds that are broken, you're going to have 3 HH bonds. So if we redo this by drawing the Lewis structures, And then these are the bonds formed, CH4 and water. So the bonds broken are 3 HH single bonds and 1 C triple bond O bond. The bonds formed are going to be 1, 2, 3, 4 CH bonds, and also 2 OH single bonds. So again, we get our bond energies from our table. An HH single bond is 436, and a C triple bond O bond is 1073. We add these two numbers together. We get 2,381. Now for bonds formed, a CH bond is 416, and an OH bond is 467. Add these two numbers together, 2,598, and bonds formed is exothermic. So we got to put a negative sign. So now our delta H is 2381 plus a negative 2598, which gives us a negative 217. So the overall reaction is exothermic. So for this question, N was equal to 1. What about, and then we formed the hydrocarbon methane for N is equal to 1. For N greater than 1, for larger hydrocarbons, do you think that the heat evolved, the delta H, do you think the delta H is going to be larger, therefore more energetic than when N is equal to 1? Or do you think it's going to be less energetic? Well, it's going to be more energetic. You're going to get a greater, let's say, a larger negative, because it's an exothermic process overall, whether N is 1 or if N is 2 or N is 3. It's just how big is the negative, basically. And you'll get a larger negative delta H, because the amount of heat evolved is going to be more energetic. So you're going to get an even larger negative delta H. So if N is equal to 2, you may get a negative 400 kilojoules per mole. That's kilojoules per mole. If N is equal to 3, your delta H may be negative 700 kilojoules per mole. So the more number of carbons that are in the hydrocarbon that you produce by the Fisher-Tropsch process, that's going to give you a more and more energy evolved, or more and more energy being released by the reaction. So your delta H will become an even more larger negative, because the overall reaction itself is going to be exothermic. And that brings us to the end of the pre-class lecture for Chapter 6 on the Fischer-Tropsch process.